Hello everyone, I'm Alex Fortuna, the team leader of ProjectRED, a team from the Department of Science and Method of Engineering at the University of Modena Reggio Emilia. Today I'm thrilled to present to you Antares, our new rover. Going into more detail about our organization, we have divided the team into two main branches, the drone part and the rover part. On the drone side, we have Marianna, our drone CTO, who oversees the technical design, development, and integration of all our drone system. She leads the drone division, which focuses on development and construction of our new drone, as well as its autonomous and manual flight routine alongside its auto-landing safety system. On the rover side, we have Nicola, our rover CTO, who oversees the complex engineering and design challenge to ensure all the rover subsystems work perfectly together. Under his management, the rover branch is divided into hardware and software division. Hardware division managed by project manager Victor Andrea Miselli and project coordinator Antonio Russo. They design, build, and optimize all the physical and electronic components of the rover. Their work range from developing the chassis and suspension for road terrain to design the robotic arm and the sample collection drill to essential subsystems like the safety system. Software division is led by project manager Frank Gino Villaneva and project coordinator Filippo Razzi. They develop the software that enable autonomous navigation and control all the rover substation, utilizing the ROS framework. They also manage robust telecommunication between the rover and the ground station to ensure optimized performance during every RC challenge. To help manage this task, this year we introduced a new role inside the technical division, the project coordinator, providing essential support to division lead alongside the managers. Supporting the team across both branches is Barbara, our operation manager, who takes care of horizontal team coordination and sponsor management. Additionally, from a couple of years now, we have expanded the team to include the Department of Chemical and Geological Science.
I'm Barbara Boccarello, Operations Manager of ProjectRED. Every year, we face new and different challenges, from solving complex technical problems on the rover to finding the best strategies to complete the competition task. Facing this challenge is exactly what makes participating in the RC such an incredibly stimulating experience for all our members.
Hi, I'm Nicola, CTO of ProjectRED. Antares builds upon the proven and robust design of Sirio. The rover features a buggy suspension system with a pair of tutti-shaped flanges pivoting around the chassis center. The system is combined with carbon fiber arms that ensure higher reliability and ease of assembly. The platform is equipped with 4 steerable wheels, carefully optimizing both size and geometry to maximize obstacle traversal capabilities and adaptabilities across an uneven terrain. To achieve a significant weight reduction without compromising mechanical integrity, extensive use of topology optimization has been applied throughout the design. The differential bar is manufactured from carbon fiber, and the custom components are 3D printed PACF, and high-stress steering flanges are produced using SLS technology with PA12. From an electrical standpoint, safety and operational continuity represent our highest priorities. Our safety system follows a strict fault isolation logic and is fully integrated into the power distribution board. The control logic remains continuously powered and is not interrupted by the emergency stop, ensuring continuous telemetry and communication with the ground station. Finally, a dedicated red button enables the 24-volt power supply for the motors, which can be immediately disconnected via physical emergency stop button in case of any hazard.
I'm Frank Jimel Villanueva, and I'm part of the software team working on our rover. The rover's software architecture is built using Ensemble, which manages communication and data transfer between the different subsystems of the rover. This includes navigation, localization, sensors, and control. To remotely operate and monitor the rover, we use a wireless Wi-Fi connection between the rover and the control station, allowing real-time communication during missions. Our rover operates using 2 main navigation modes, autonomous and manual. In autonomous mode, the rover navigates independently using a localization system based on Aruco marker landmarks placed in the environment. These landmarks allow the rover to estimate its position accurately while moving. To safely traverse the terrain, a front-mounted depth camera continuously detects obstacles, enabling the rover to avoid collisions and plan safe paths in real time. In manual mode, the rover can be directly controlled using 4 different driving configurations: crabbing, swerve, turn on spot, and differential drive. The primary modes used during operation are swerve and turn on spot. Swerve drive allows smooth omnidirectional movement and precise steering, while turn on spot enables the rover to rotate around its own axis for fast orientation adjustments in confined spaces. Together, these systems provide both autonomous capability and flexible manual control for different mission scenarios.
Hi everyone, I'm Marianna, CTO of Drone Division, and I'll walk you through Acrab, the drone we built for the ERC 2026. Our drone is a custom-built quadcopter on a 5-inch carbon fiber frame that we are adapting to a 7-inch. We chose this solution for its rigidity and payload capacity. All onboard components, computing, sensing, and battery are housed in a custom 3D printed enclosure, keeping everything securely integrated and protected. On board, a Latte Panda Sigma runs our MATLAB-based logic, paired with an Inter-RealSense depth camera for real-time RGB and depth perception. Power comes from a 6S lithium-ion battery, ensuring reliable endurance throughout the task. One of our key design choices was building a hybrid control architecture. The autonomous logic runs on the Latte Panda and sends commands to the flight controller in the same format as RC signals. A dedicated switch on the transmitter lets the pilot select the flight mode at any time. For instance, in manual mode, the RC input takes over, blocking the autonomous commands. This means we never lose the ability to intervene. The system also includes a fail-safe mechanism. If the autonomous logic fails or the RC link is lost, the flight controller automatically triggers a safe landing. System state is always visible at a glance through an onboard LED indicator. We are currently implementing the detection pipeline. The drone will follow a predefined scanning path to map the entire competition area, detecting both the probes and the landing target in a single pass, then navigate directly to land on the identified target. We are also developing a custom landing platform attachable to our rover, designed to receive the drone after landing and keep it protected during rover operations.
Hi, I'm Andrea, Division Leader of Low-Level Communications at ProjectRED. This year, our entire rover is fully integrated over the CAN Open protocol, powered by our custom libraries. We upgraded every single subsystem to act as a direct, independent node on the CAN bus. This drastically reduced our wiring and unlocked true plug-and-play modularity. We developed a deep sampling system with a multi-stage deployment. An electric piston first shifts the unit from a stoved position into its vertical working stance. Then, a stepper motor controls the linear descent, while a DC motor drives the drift rotation, reaching depths up to 13 centimeters. Once the soil is collected, a dedicated servo motor mechanically seals the storage case, guaranteeing the sample to be completely secured. Our science box features a built-in sieve that mechanically separates rock from sand, allowing our load cells to accurately measure both of them. Regarding the manipulator, we introduced a custom-built force sensor to provide real-time feedback and a new smart end effector. Mechanically, it is a highly versatile, featuring modular and interchangeable interfaces. The electronical part integrates a custom STM-based PCB, performing admittance control by reading an FSR matrix mounted on the fingers. In addition, the system manages a time-of-flight sensor. This upgrade is crucial. It actively assists in object detection and makes the arm's high-level control more reliable and autonomous.
Hi, I'm Matteo Bicchi, robotics specialist for the team ProjectRED. I'm responsible for the development of the control software for the robotic arm. This year's focus was mostly towards autonomy. We developed a pipeline to easily train small YOLO models, starting from a limited number of input images, while still achieving great accuracy over different light conditions. We used these models together with Aruco detection and depth data coming from the end effector to create a series of algorithms that were able to uniquely identify each element of the maintenance panel. Combining this with the Manipulator API that we developed last year, we created a set of routines that were able to autonomously operate the maintenance panel with great reliability. We tested everything out on a collaborative robot to rule out any mechanical imprecision and focus solely on high-level control.